Welcome, builders, to the drafting room. I am your chief architect for today's session, and let me tell you, you are stepping into a high-stakes, industrial-grade workspace right now. This isn't your average run-of-the-mill tutorial. This is a high-rise exam construction blueprint workshop. We are tackling a mathematical structure that appears in absolutely every single examination series. I am talking about Cambridge 9709 Mathematics, specifically the 1.6 series. We're diving deep into the ironwork of geometric progressions, convergence, and the sum to infinity. Now listen closely, because mastering this 1.6 series is not just about memorizing a few flimsy formulas from a textbook. No way. It is about engineering a flawless structural response that can withstand the absolute ultimate force, the principal examiner's red pen. My job today is to teach you exactly how to lay down an unshakable thesis foundation, how to erect load-bearing analytical arguments, and how to construct structural mathematical connections that will literally survive the most rigorous examiner's stress testing imaginable. In this architectural firm, we reject poorly framed sentences instantly. I see students all the time acting like builder number one. Let's call him Alex. Alex just stacks up way too many heavy bricks of raw facts without ever checking if the steel frame can actually support that weight. Or they act like builder number two, Sam, who wants to put up all these shiny glass panels and decorative features before even cementing the foundational mathematical columns. We are not going to make those critical errors. The construction deadline clock is ticking, so grab your hard hats and let's get to work. Let's quickly review the master blueprint agenda for today's build. We are breaking this construction down into 4 distinct phases. First up, the foundation, core principles. Second, the procedural technical framework. Third, critical analysis and evaluation. And we finish up with phase 4, examiner warnings and stress tests. All right, let's fire up the drafting screen and move straight into phase 1, the foundation core principles. I want you to really let this crucial insight sink in. This comes straight from the senior examiner, our ultimate site inspector. Quote, even if your final answer is wrong, method marks can save you, end quote. I absolutely need you to internalize this concept today. Think of it like this. In the rigorous architecture of advanced mathematics, if you are dealing with a massively complex sum to infinity problem and you happen to miscalculate a single tiny decimal at the very end of your build, well, if your underlying algebraic setup is fundamentally sound, your structure remains standing. A strong structural process literally saves the building, even if the final cosmetic exterior has a slight noticeable flaw. The rigorous mathematical process is the reinforced concrete that guarantees your grade doesn't collapse. So, mastering what we call the method mark strategy is your absolute highest priority. What does this actually mean on the ground? It means earning points for the structural, mathematical process and execution, totally independent of the final numerical output. Top-performing candidates, the true master builders, focus intensely on this load-bearing conceptual understanding. They are not just desperately hunting around for the right final answer to write at the bottom of the page. No, when you are proving convergence in a geometric progression, the examiner wants to see the specific, connected architectural logic. They want to see exactly how you identified the common ratio. They want to see the exact moment you established that its absolute value is strictly less than 1. And they need to see precisely how you set up that sum formula. Every single beam must connect seamlessly to the next. Now, to enforce this level of quality, Cambridge uses very strict building regulations. We call these the assessment objectives, and they target 3 distinct cognitive domains: knowledge and understanding, application, and analysis. Think of knowledge as your basic drywall, application as your wooden framing, and analysis as your reinforced structural steel. If you build a purely descriptive structure, meaning you literally just write down the formula for a geometric progression and plug in some numbers without explaining the why, you are only hitting that knowledge level. It's just drywall. And what happens? That structure collapses instantly under the weight of higher tariff mark scheme criteria. To reach the application and analysis domains and secure those top-tier points, you have to demonstrate established principles. You need systematic analysis and evidence-based reasoning to securely rivet the structure across all 3 of those domains. Okay, we are shifting gears and moving smoothly into phase 2, the procedural technical framework. We have poured the conceptual foundation, so now it is time to erect the actual technical framework of a 1.6 series response. I am bringing up a complex, high-tariff Cambridge past paper question on the digital blueprint screen right now. Consider this your foundational challenge. To beat it, here is the exact 5-step procedural framework you require. Step 1. Deconstruct the question. You have to find the exact command words. These are your command stress points. Step 2. Extract relevant data. In our world, that means physically isolating the first term, A, and the common ratio, R, from the noise of the word problem. Step 3, select your analytical framework, which here is the specific mathematical condition for convergence. Step 4, execute with clear notation. This means your equal signs are perfectly aligned down the page like the steel girders of an elevator shaft. Step 5, present with correct terminology. Guys, you absolutely cannot skip steps here. If you build a descriptive structure instead of an evaluative one, you fail. You must first deconstruct that prompt, extract only the necessary load-bearing variables, explicitly state your convergence condition, and only then execute with precise algebraic notation. That is exactly how you align your paragraph columns to the Cambridge mark scheme.
Excellent work. We are now entering Phase 3, Critical Analysis and Evaluation. Consider this our official ironwork peer debate. Just the other day at the drafting board, I was watching two of our junior builders, Alex and Sam, trying to construct a model response paragraph for a geometric progression. Let's compare a fragile, standard candidate's approach with a load-bearing, top-scoring one. Alex, our standard candidate, says to me, "Hey, Chief, I'm just going to write down every formula I know and dump the numbers in." I had to tell him, "Alex, that's a massive unreinforced cement block of pure raw math. It's going to crack because it lacks a flexible steel frame." Then Sam chimes in and says, "Well, I'll just write a very eloquent paragraph about how the numbers get smaller." And I had to say, "Sam, that's a beautiful glass window, but you have zero load-bearing columns. You completely missed the mathematical command words." Both of their structures had zero flexibility to hit top band scores. The load-bearing, top-scoring candidate does something completely different. They demonstrate true evaluative thinking. They dynamically question assumptions, they leave hollow space for counterarguments, and they justify their decisions with solid, irrefutable mathematical evidence. When a master builder sees a geometric progression, they don't just blindly assume it converges. They explicitly justify exactly why it converges using rigorous, step-by-step evidence. Hold on, freeze the blueprint animation, site inspection. Before we pour this final layer of text concrete and secure this high-scoring paragraph framework, you need to make sure your construction line is permanently reinforced. Hit pause and subscribe to Ace the Exams at the handle @AceTheExams right now. Turn on all notifications so you receive our weekly structural grade upgrades. Seriously, whether you are building a foundational IGCSE bungalow or erecting a massive A-level skyscraper, this channel is your primary grid. Okay, inspection over, let's get back to the build. To secure your marks, you must explicitly state your assumptions based on 4 core principles. Identify limitations, state assumptions made, consider alternative interpretations, and assess the effect on conclusions. If your evidence beam fails to latch onto the main thesis column mid-paragraph, you need to use the Peel methodology. Point, evidence, explanation, link. You have to extract the data, interpret those complex relationships, and explicitly rivet your mathematical evidence back to the conclusion that the series converges. If you apply the sum to infinity formula without proving the absolute value of r is less than 1, your logic beam completely snaps under the pressure. Let's move right into our final stage, Phase 4, Examiner Warnings and Stress Tests. I want to address you directly for a live site safety audit. I call this the blueprint matrix. Imagine a complex source data chart displaying a wildly fluctuating geometric sequence from a highly difficult recent past paper. I'm putting a mental 60-second visual countdown timer on the clock right now. Look at that data in your mind's eye. What is the single most high-yielding core metric needed for your construction? Why do student structures collapse under examiner stress tests in exactly this scenario? 3, 2, 1, time's up. If you didn't immediately identify that you need to explicitly isolate the common ratio r and test its absolute value against the number 1, your entire methodology just failed the safety audit. Those specific data interpretation skills, the ability to extract and interpret relationships securely and quickly while under the timer, that is the exact difference between a standard passing grade and a towering top-tier result. Now let's look at the hard data coming directly from the site inspectors themselves. I have personally combed through the Cambridge Principal Examiner reports for the 1.6 series, and I am revealing the top 3 structural roadblocks that cause instant point deductions if you ignore the building regulations. Warning number 1, forgetting proper format. Students lose incredibly easy marks by dropping correct terminology when defining their geometric progressions. Don't be that builder. Warning number 2, failing to check format and presentation. This means submitting sloppy notation where a beautiful series formula is practically indistinguishable from a simple, messy algebraic jumble. The inspectors absolutely hate that. It looks like a hazardous work site. And warning number 3, answers not specific to the given context. Listen carefully. If the exam question frames the sequence around a real-world financial depreciation model and you simply spit out a generic algebraic proof without linking it back to that specific financial context, your structure is immediately rejected for being non-compliant with the blueprint. And that brings us to the absolute most critical warning of all. Examiner alert. Show you're working. Unseen foundations will collapse. I cannot stress this enough, team. Students consistently lose massive marks by not annotating their foundations.
Imagine an inspector walking onto a construction site and seeing a skyscraper hovering 10 feet in the air with no visible steel columns. They aren't going to say, wow, magic. They're going to shut the site down immediately. We talked about the method mark strategy earlier, but this is where the rubber truly meets the road. If you do complex mental math and just confidently write down the final converged sum, the examiner cannot verify your foundation. You will get 0 method marks. 0. Every single derivation, every extraction of A and R, every single substitution into the sum to infinity formula must be clearly annotated on the page. Hidden structures inevitably fail the stress test. Remember this, your final cosmetic answer might be wrong due to a completely silly arithmetic slip. But if your perfectly annotated working shows a flawless conceptual understanding of the 1.6 series framework, those method marks will step in and save your entire grade. So we roll up the plans, the blueprint is complete. But I leave you with this final provocative thought. Will your 1.6 series methodology actually survive the final exam stress test? You now possess the tools. You have the procedural framework, you understand the load-bearing requirements, and you have the inside examiner insights to build a mathematical structure that absolutely commands top marks. But just knowing the blueprint isn't enough. You must pour the concrete yourself. Your site assignment right now is to take this rigorous structural framework and apply it directly to past papers. Build the response, test it against the mark scheme, fail, figure out exactly why it cracked, and rebuild it stronger. Keep practicing those past paper questions, master your method marks, and I will see you back here in the drafting room for the next masterclass. Keep building.